In this video, we are going to discuss about analog to digital converter. Take analog as an input, and with reference to V reference, it converts into a input analog signal into a digital output. Suppose, let's say we have an analog signal xt using the sampler. So it has been sampled. This is where the sample and hold circuit are used. Now we can quantize this sampled value, which means a sampled analog signal will be replaced with an approximation from a finite set of discrete value. So we say sample is quantized. Sometimes this is also called rounding. Analog to digital converter. So on x-axis we have analog values, on y-axis we have a corresponding digital values like digital code 000, 001, 010, 011, 100, 101, 110 and 111. VFSR. What is VFSR? It is full scale range input, and they are actually related. Full scale range input is actually related with the V reference that we also discussed earlier as M into VRIF upon gain, where M is the reference voltage scaling factor and gain is the internal gain. Now the resolution of the ADC. Basically, entire input range is divided into a number of subrange, also called as step size, sometimes also known as LSB or least significant bit, which is usually defined as VREF or VFSR upon 2 to the power n. So 1 LSB is actually the minimum change in input needed to cause a change in digital count. Now transfer characteristic for an infinite resolution ADC is a linear function, a straight line, while case for actual or let's say finite resolution, also ideal, is staircase, because now the resolution is limited. It depends on the number of bits that it has. More quantity known as VIFS, also known as voltage full scale input voltage, also known as full scale input voltage. So it is basically VIFS is the maximum input voltage that will cause all logic 1 at ADC. So it is the voltage corresponding to which it will generate 111, or all code will be or binary digit will be 111. So if we see from the graph, VIFS is actually VFSR minus 1 step size, which is 1 LSB, and we know VFSR is actually and we know that LSB is VFSR upon 2 to the power n. So it will eventually be 2 to the power n minus 1 into VFSR upon 2 to the power n, which again will be 1 LSB. So VFSR actually equal to 2 to the power n minus 1 LSB, or LSB equal to LSB equal to IFSR upon 2 to the power n minus 1. Now let's discuss about quantization error. Next parameter, quantization error. It is actually the difference between an infinite resolution characteristic, sometimes also called ideal, and the actual characteristic. So if we plot quantization error, it will be like a sawtooth wave. So quantization error will be 1 LSB. The one way to reduce this quantization error, also called, maybe sometimes also called adjusted quantization, is to shift the transfer characteristic towards the left by 1/2 LSB. Now if you plot this quantization error as plotted with a red color, and also the shifted transfer characteristic is plotted with the red color. Now the quantization error will be actually plus minus 1/2 LSB. Now next parameter, offset error. It is actually the difference between actual transfer characteristic and perfect, sometimes also called perfect transfer characteristic at the point of 0. So it is also sometimes called zero scale error. So let's see what do we mean by offset error. Let's draw its transfer characteristic. On axis we have analog input, on y axis we will have digital output. And then we have an ideal transfer characteristic, or finite resolution ideal or perfect transfer characteristic, and we have a characteristic drawn with a red color which has an offset error, because of which the all characteristic has been shifted by 1 LSB towards the left. So if we see at the 0 input, we still see a digital code corresponding to 001. So this is because of the presence of offset error, and we can find of this by applying a 0 voltage. If it is generating some code, it means it has an offset error, and if not, we will get some other code, and we can subtract that code to get our actual code. The next parameter is gain error. This is usually measured or corrected after measuring the offset error, after correcting for the offset error. The slope of the actual transfer characteristic deviates from the ideal characteristic slope, then we have a gain error. And again, it is the difference between voltage at which it will give full scale output code, usually 111, and the ideal transfer characteristic. So it is usually measured at the extreme right hand corner. It means the voltage which will generate 111 code, and at that voltage what's the difference between actual and perfect transfer characteristic. Let's see how it should look like. Again, a transfer function. On x-axis we have analog value, on y-axis we have corresponding binary, and then we have a perfect ADC transfer characteristic. Now with the red we have drawn other transfer characteristic which slope is different from the ideal case, and also the corresponding staircase characteristic is also drawn. So at the voltage corresponding to when it will generate 111 code, so there is actually difference between them. So at this value, the difference between actual and the perfect characteristic is gain error. The next error is non-linearity. This is after correcting for the gain and offset error, and it is of two types: DNL, differential non-linearity, and integral non-linearity. Differential non-linearity is actually difference between step width of actual and the perfect transfer characteristic for adjacent code. Suppose the black characteristic is perfect transfer characteristic, and the red one is actual transfer characteristic which has this error, and DNL we can calculate as we also mentioned earlier, the difference between actual and perfect step size for adjacent code. Like for example, the red one step size is 1.25, but ideally it should have been 1. So 1.25 minus 1 equal to 0.25. So DNL is 0.25. For the second transition, it again step width is 1.25, and ideally it should be 1. So 1.25 minus 1 is 0.25. Now, and next it's actually made a vertical jump without making any progress in a horizontal side. So basically in horizontal direction it is going nowhere, so step width is 0 and ideally it should be 1. So 0 minus 1 is actually minus 1. So differential non-linearity is minus 1. And the next step width again is 1.25, and again subtracting minus 1 it will be 0.25. Next it made again 1.25 and again minus 1, so 0.25. next step width is equal, so it should be 0. Now, so whenever there is a DNL is actually greater than 1 or 1, there will be actually a missing code. So with this transfer characteristic we will not be able to generate any code corresponding to 0, 1, 1. So it is missing. So if the differential non-linearity is greater than or equal to 1, there will be a missing code. The second kind of a non-linearity is integral non-linearity. It is actually deviation of actual transfer function from straight line. And that straight line could be best fit line, or it could be line connected end to end point. So again, if we draw xi characteristic, on x-axis we have analog input, on y-axis we have a digital output, and we have a black color curve which is perfect transfer characteristic, and we have drawn a end-to-end line. And with the red line we have drawn is the actual transfer characteristic. So now let's calculate the INL, integral non-linearity. So at first transition, the difference between the straight line and the black corresponding to black transition, black curve, is actually 0.5. Similarly, for the next case also it is 0.5, the gap between the black and red line at the transition. Next is 1, then again it is 0.5, and then the transition is happening at exactly the same. So INL is actually 0. Then another parameter is settling time. It is actually the time required following an analog input step change, usually full scale, for ADC to reach and remain plus minus 1 by 2 LSB. And then another parameter is monotonicity. If its transfer characteristic either increase and remain constant, it's said to be has the monotonic or has the monotonicity. If it is decreasing, then it is called, or this is said to be having non-monotonic behavior.